This is Black Hole Radiation Decoding is Quantum Cryptography. I'm Brakerski. I'm really sorry I couldn't be with you at the conference. I'll try to tell you a little bit about this work from remote. So this work is about black hole radiation, in particular the quantum nature of Hawking radiation. So we have like a black hole here, as you can see, and the middle of the black hole is called singularity, and there's a lot of gravity there, and nobody knows what's going on. The boundary of the black hole is called the event horizon. And at least for a large black hole, the event horizon does not have like extremely high gravity. So physicists think that they have this effective field theory that describes what's going on near the event horizon. And when people do the analysis in the 70s of the area of the quantum analysis, quantum field theory analysis of the event horizon, they saw that there's supposed to be some radiation. So if you just make a black hole and leave it be, it's going to start radiating and radiating until in the end it's going to evaporate. So for us, we're going to take the sort of quantum information theory approach here and just think about everything that's going on as qubits. So we can think about the universe as consisting of three subsystems. One is the inside degrees of freedom of the black hole, so we denote this by H. The outgoing radiation I'm going to denote by B, and we're just going to assume that the black hole radiates one qubit at a time. So it just starts emitting qubits. And then we said that we have a black hole that's been around for a while. We can think about the radiation that has been emitted in the past. So, the universe made a black hole, it started radiating, and then we look at it at some point in time. In particular, we're going to think about some point that's after a half of the expected of the lifetime of the black hole. And we're going to look at these three subsystems. And these three subsystems consist of the entire universe, and therefore it's a pure quantum state. So we assume that the universe evolves unitarily and efficiently, computationally efficiently. Now, another consequence of quantum field theory is that the outgoing radiation is going to be maximally entangled with ingoing modes. So for any qubit that's emitted of the black hole, there's going to be a qubit that is sort of sent inside into the black hole. So one way to model this is that the black hole radiation is like EPR pairs, and one half of the EPR pair is being emitted out, and the other half sort of stays inside the black hole. And that brings up a problem, because if you look at this outgoing radiation B, then on one hand, as I told you now, quantum field theory says that this qubit is supposed to be maximally entangled with the inside degrees of freedom, with H. But on the other hand, if you think about it entropy-wise, once the black hole is sort of old enough, there aren't sufficiently many degrees of freedom inside the black hole, and it has to be the case that this outgoing radiation is going to be essentially maximally entangled with the outside, with the radiation from the past. And of course, this is a conundrum because of the monogamy of entanglement. So we can't have this qubit being entangled with two different systems. And one way to try to resolve this conundrum is to say, well, if R and H are both maximally entangled with B, then maybe both of them are actually two manifestations of sort of the same Hilbert space. So these are actually sort of secretly the same system. And one is inside the black hole and one is outside the black hole. So it should be fine. We're never going to sort of have any, we're never going to actually see any conflict. However, the firewall paradox of Al-Mihiri et al. Actually suggests a thought experiment that would allow you to potentially witness the monogamy of entanglement violation from this setting. So we can't just sort of hide behind the excuse that these two systems are never going to sort of interact. So the firewall paradox, the thought experiment, is the following. So we're thinking about an experimenter, Alice, and she sits outside the black hole, and she captures all the radiation that comes out of the black hole. So she has sort of control of R. And then Alice she also knows how the universe evolves, so she knows the laws of nature. So she knows what is supposed to be the next qubit that comes out of the black hole. So she can distill from the old radiation that she has, the qubit from the old radiation that is supposed to be maximally entangled with the next outgoing qubit. So she distills a qubit D such that B and D are supposed to be maximally entangled. They're supposed to be an EPR pair. Then as B comes out, so Alice sort of waits for B. She waits for it to come out of the black hole. She measures, she checks that indeed B and D are maximally entangled, and then she jumps into the black hole to find the sort of the EPR partner in the entangled mode. So for this, she's looking for this black arrow, and witnesses the monogamy of entanglement. And the conclusion of Al-Mihir et al. Is that there should be some firewall. There should be some like high energy barrier, perhaps at the event horizon, that sort of prevents this entanglement with the inside modes. And this is in some sense undesirable because I think the physicists want the sort of this effective field theory. So they think that there's this effective field theory that works until you hit some energy cutoff, and this is supposed to work at the area of the horizon. So it would have been good. It would be good if this was indeed the case. So try to get around this sort of undesirable consequence. And one way out that was proposed by Harlow and Hayden was to notice that this process here, that Alice distills could be and is in general computationally intractable. So it can take a long time for this to happen. And at this time, perhaps the black hole evaporated, or the sort of ingoing mode reaches the area of the singularity in which we are not supposed to be able to say anything. So perhaps this sort of computational argument is supposed to save us. And so how do you sort of fit it into the actual physical argument? So the way I understand it, Harlow and Hayden actually suggested that if you have an effective field theory, then in addition to an energy cutoff, so you want to say your theory is not applicable beyond a certain energy level, you're also saying that it should not be applicable if you manage to sort of break some computation barrier. So if you can solve a computational problem with fewer resources than you're supposed to, then sort of complexity theory it tells you that you should. Yeah, another way to try to think about it perhaps is that maybe you can sort of fit this into the energy cutoff. So maybe you can somehow argue, and I actually I don't know if this is in the literature, maybe you can somehow argue that if you try, if you're very lucky and manage to solve a computational problem with lower complexity than you're supposed to, then this requires you to go above the energy cutoff. So you need to bring so many resources that actually you have to cross the energy cutoff, and then sort of the effective field theory is not supposed to apply, and sort of we can at least be happy with some low energy theory that is applicable in the regime of the event horizon. So, but for the purpose of this talk, we're adopting this framework of Harlow and Hayden, and we're trying to understand the connection, the computational complexity of this decoding problem. Okay, so we're defining this black hole radiation decoding problem. In this paper, we call it BHRD, black hole radiation decoding, or Harlow-Hayden decoding. And the problem is as follows. So you have a setup procedure, which have this sort of universe generating the black hole. So it's an efficiently generated quantum state over three subsystems, H, B, and R, where B is a single qubit. And we have a promise that B and R are maximally entangled. So there exists some process, inefficient process, that distills from R a qubit D, such that B and D are an EPR pair. So this is what we're promised by sort of the universe. And now the input to the problem is access to the register R. So we get access to the sort of the old radiation, and we are required to actually output this distilled qubit. So we want to output the register D such that B and D are maximally entangled, and actually it's going to be enough for us to get to output a D such that B and D are correlated. So if B is maximally entangled with the ingoing modes, then it's not supposed to have any correlation with anything that's outside the black hole. So in order to witness a monogamy violation, it's enough to witness that B and D are correlated in some arbitrary way. So our goal is to be able to find correlations essentially between B and R. And Harlow and Hayden actually shows an example. So they show that you could generate some states such that doing this, and they were considering the setting of trying to recover the sort of the EPR partner, and they showed the SDK hardness. So Harlow and Hayden actually showed that if you can do this, then you can solve problems that are complete in the complexity class statistical zero knowledge, which is assumed to be intractable. And Aronson sort of related this to cryptography, and he showed that if there exists these cryptographic objects called injective one-way functions, then you can also generate some such states such that it's hard to find the EPR partner. So everything sort of went in one direction, showing that if you assume hardness, if you assume computational hardness, then you have sort of an instance of this black hole radiation decoding, which is hard. So what we do in this work is sort of complete the picture and show that this task of black hole radiation decoding is actually sort of identical to some cryptographic task. So let me sort of elaborate more. So the first thing that we do is provide a quantitative definition for this BHRD problem. So in prior works, it was sort of more in the air. And again, sort of it wasn't really defined whether you're supposed to find the EPR partner or just find correlations. I think it was just assumed that the people were talking about the EPR partner. So here we actually sort of provide a definition for this problem. There's also an issue of whether you need to define as an average case problem or worst case problem. So we deal with that as well. And then we show sort of an existential equivalence between this problem, this black hole radiation decoding problem, and sort of a minimal quantum cryptography object. And this quantum cryptography object is potentially weaker than one-way functions. So one-way functions are sort of the basic, the weakest, in some sense, classical cryptographic object. But in recent years, we actually sort of realized that if you allow quantum information and quantum communication, then you can create cryptography even under assumptions that are weaker than one-way functions. So even things that, even for objectives that require computational assumptions, you can do with assumptions that are potentially weaker than with cryptographic objects that are weaker than this one-way functions. And in particular, this improves upon these prior works that sort of were working with one-way functions. So specifically, what is this object, right? There's an object and so forth. What is this object? So we show that this BHRD hard state exists if and only if we have EFIs, or non-interactive statistically binding commitments. So this cryptographic object that we're talking about is equivalent to black hole radiation decoding is this EFI. So this is there's two things that are actually shown to be equivalent. So non-interactive statistically binding commitment is a form of a commitment scheme, which is sort of something that's pretty standard in cryptography. But recently we showed that this is there's a way to potentially easier way to think about it. So we can just think about this object called EFI. And EFI are just sort of describes two efficiently sampleable distributions over quantum states. So you have like sort of two-state generators of mixed states. And these mixed states are supposed to be statistically far. So if you have unbound computational power, you should be able to distinguish them, but they're computationally indistinguishable. So this is a cryptographic object, and you can actually show that its equivalent, so this sort of very basic definition, is equivalent to various cryptographic primitives. So for example, non-interactive statistically binding commitments. So we're going to talk about commitments in a little bit. Oblivious transfer and a bunch of other things. So and now we show that this is also sort of this object that really sort of naturally comes up when you find this black hole radiation. The other thing we show is amplification register D such that B and D are correlated, and we measure this using the fidelity between B and D and an EPR pair. And you can think about an easy variant to find any non-trivial correlation, or a hard variant, which is to find a near EPR correlation. So you can think about two variants for this problem. And we show some amplification theorem that shows that sort of even if the hard variant is hard, then you can get EFI. And if you have EFI, then you have the hardness of the easy variant. And sort of recently, Bostanci et al. Showed an amplification theorem for EFI that should allow to improve this thing and actually consider an even harder hard variant. Even that is going to imply EFI. So that's good. So let me sort of just give you like a very high level idea of what we're doing. So we want to show that quantum cryptography implies quantum gravity. So we're assuming this object that's called non-interactive statistically binding commitments. And sort of a commitment scheme is like a locked box, right? You have your information, you put it in a box, you give it to someone, and then when you want to open, you just give them the key, and then they can sort of see what was inside the block commitment. And this has been shown to be equivalent to EFI, and also plausibly it exists even if one-way functions do not exist. So our approach here is sort of following in the footsteps of Harlow and Hayden and of Aronson. And what we're going to do is we're going to sort of start with, so this is this non-directed statistically binding commitment allows you to use quantum information to commit to a classical bit. However, what we want is to be able to commit to a qubit. So what we're going to do is sort of commit to, we're going to generate B and D as an EPR pair. And then instead of sort of releasing D, we're going to release a commitment to D. So the subsystem R is going to be a commitment to the qubit D, and its opening is going to be hidden inside the modes H that are inaccessible, subsystem H that is inaccessible to the adversary. So the adversary is just going to get a commitment. And what do we want from this commitment? So first, we want this notion that's like, you can think about as quantum statistical binding. So this allows for information theoretic inversion. So that the information that you have in R, actually information theoretically completely determines D. The second thing is hiding. You want to be able to computationally hide all information in D, which means that in the eyes of the adversary, he gets R, but actually it's computationally indistinguishable from not getting any information about D. So he might as well have gotten a commitment to something that's completely unrelated to the qubit B, so he should not be able to find any correlations. And the way to achieve this quantum commitment, so what we do is we start from, again, quantum commitments to a classical information and derive quantum commitment to quantum information, essentially by using the quantum one-time pad. So this is like the approach that you could think about, and you would think about. So in the opposite direction, right, we start from quantum gravity and want to get quantum cryptography. So our goal is to create EFI, so two indistinguishable distributions. What we have is an instance of the black hole radiation decoding. And the challenge here is that the interface of these two problems is different. So in the black hole radiation decoding, the output, like what the adversary gives you, is actually like a qubit. So it gives you quantum information, whereas in the EFI problem, you need to distinguish between two distributions. So your output is just a classical bit. So we need to sort of find a way to translate, so to take an adversary that gives you like this quantum information and convert and find a way to sort of embed in this quantum information, this EFI challenge, so that when we get the quantum response, we can actually sort of distinguish these distributions. And what we do is essentially find this classical hardcore bit for the black hole radiation decoding problem. I'm not going to get into details. You can see in the paper, but the intuition sort of comes from teleportation or super dense coding. So in some sense, we sort of fool the adversary into sort of teleporting the output. The adversary thinks that it's sort of giving us a qubit, but actually it's giving us a classical information that's sort of super dense encoded in this qubit, and this is sort of how we get this reduction. Then we amplify via parallel repetition. And as I mentioned, this new parallel repetition theorem of Bostanji et al. Can actually be used to get a stronger result. So the last thing that I want to talk about in the minute that I have left is some sort of a high-level sort of consequence of this potential consequence of this work, and it's sort of more philosophical and sort of more arguable, so might not agree, but let me sort of try to put it out there anyway. So we think about one-way functions. So one-way functions are these sort of very basic primitive where you have a function that's easy to compute and hard to invert. What does it mean that it's hard to invert? So that the computational complexity is high, which is supposed to be some proxy for requiring a lot of physical resources like time and energy in order to invert this one-way function. So why do we think that these objects exist? Why we use them in cryptography? Why I think that they exist? Well, the first thing that we mostly do in cryptography, there are some math problems that we don't know how to solve, like factoring, and a lot of smart people tried to solve them for a long time and didn't succeed. So we use the intractability of these computational problems in order to sort of obtain one-way functions. But we could be wrong, right? Maybe we were just silly and we haven't figured out a way to solve factoring. And sort of this is always sort of lurking in the background. Another way to try to approach this problem is to say, well, we can think about some processes in nature, such as scrambling an egg, that seem to be one way in sort of nature. So we can try to sort of rely on those in order to get a candidate for a one-way function. And again, in this case, we can again, so with this black hole radiation is sort of one way to think about it, right? You have like this black hole radiation decoding problem, and if indeed this is a correct model of the universe, and if indeed the universe requires this black hole radiation decoding problem to be hard, then maybe we get some quantum cryptography out of it. But you can think about other physical processes here. And yeah, so you can never actually sort of get a proof for this thing, but you can sort of try to argue that if we have a sufficiently good model for the laws of nature, then you get this. Then this implies hardness for your candidate. And again, so the laws of nature, maybe we didn't get them right, but we actually have like this process called science that allows us to sort of validate our current estimate of the laws of nature. So we can do experiments and we can do observations and so on. And this is sort of my point is that this is sort of a different process. So at least it's like a different justification, a different way to justify why we should believe that one-way functions exist. So all I'm saying is that this is sort of another, this is interesting also in sort of providing us for another path. So we cannot sort of get a hard proof, because we can never be sure that our model for the laws of nature is correct, but it's sort of still nice to get some sort of, again, independent evidence for this. So I'll wrap up. So these hard problems come up in nature, possibly essential. It could be a physical argument for cryptography. Harlow and Hayden show that computational hardness can censor the violation of monogamy of entanglement. In this work, we showed that this is a two-way street. So this is actually equivalent to some cryptographic objects. And perhaps this phenomena also appears elsewhere, might be worth looking into it. Thank you all very much. Yeah, I'm hoping everybody's enjoying the conference. Too bad I can't be there with you. Bye.